Okay, and Sue, one thing just to add to Chris's comment is, gene therapy has been around for a long time, AAV gene therapy and lenti gene therapy. Lenti has actually been around in more numbers of trials than AAV gene therapy. And when you go to gene therapy and cell therapy conferences and you hear, scientists, world-renowned scientists talking about treating patients and outcomes, you rarely hear the word cure. And cure is a really quite a optimistic word and a hard word to use because the reality of that is hard to even understand. But when you look at disorders like SCID, which is what he showed, which ultimately is where you're completely immunodeficient and you universally die by the age of 2 if you don't have a bone marrow transplant of someone else's cells or some type of gene replacement therapy, and then see that they're 95 to 99% have been totally cured of SCID with needing no therapy at all after the gene therapy, scientists start using the word cure. And that was one of the most eye-opening things that I ever saw, which was for lenti, hearing for MLD, which is a neurologic disorder, CALD, another neurologic disorder, cystinosis, MPS, all the neurologic forms. All of these people got up on the stage, well-renowned scientists, and said, we've cured these patients. And you don't hear that often. So I think cures are aspirational, and we should all remember that. It is our tagline, and we're aiming for that. But it is aspirational. Meaningful change is what we all want, and one day we're going to get there. But hearing people use the word cure is something that takes your breath away when you hear it. So it's very optimistic. Okay. So our next speaker is coming to us on Zoom, who is Dr. Nadav Ahituv, who is from the University of California, San Francisco. He's a professor of bioengineering, and he's going to be speaking to us about the CRISPR activation strategy that we talked about for the genes outside of UBE3A. And he has a very novel strategy in which we can try to think about this for the deletion population. Nadav?
Thanks. I don't know if you can hear me well.
Yeah, we can hear you.
So I guess next slide. So my lab works on gene regulatory elements, so just a quick 101 on regulatory elements. So if we have a gene, and next, and the gene is sort of like a light bulb and turns on, and right next to it, next, is the promoter, which is sort of an on-off switch. And so if somebody can click next, that would be great. And then far away from that, distances are what's called enhancers. These are sort of the dimmer switches of the promoter. And next. Now, I guess we can go to the next slide. So, we're interested in basically taking advantage of these regulatory elements to turn on or off or increase expression of genes, and we think that could get therapeutic for a variety of different diseases. Next slide. Next, yeah. Cool. So the first disease that we started going after is what's called haploinsufficiency. Haplo is half, insufficient is not enough. And basically we have 2 genes, one from mom and one from dad. Next. And that should give us large levels. And next. And next one. And every so often we can have one gene that is a loss of function. So we only have one copy of the gene that's functional. Next. That gives us basically 50%. Next. And then there are 660 genes basically that when you have one copy, that is the human disease, because there's only 50% of the protein being made. And next. And it's estimated that there's even 3,000 genes based on sequencing data from all genes. Next. Next slide. So basically, you've all heard about CRISPR, and CRISPR can cut the DNA, but there's another form of CRISPR called the dead-Cas9, where the scissors have 2 mutations, so it doesn't work and cannot cut the DNA, but you can bind to the DNA. So you could use it as a delivery drug to basically bind to a certain location, like a regulatory element that I mentioned before, and you can attach an activator to it that will basically force it to force the gene to make more RNA, and that's the help CRISPR activation. Next slide. So next slide. And so the idea here is we still have a functional copy, it's just giving us 50%. So if you target it with CRISPRa, next, you might be able to upregulate expression, and that might be able to rescue the phenotype of haploinsufficient disease. Next one. Next, yeah, all the way to the next slide. Yeah, sorry, I have too much animation. So this seems to work very nicely, and we showed this a few years ago to work on obesity, which was a good model for this, because all we had to do was measure the mice, and you can see on the left a mouse that has one copy of the gene and is extremely obese, and in the middle there's a mouse that has exactly the same genotype, meaning it has one copy of this gene and should be extremely obese, but you can see that because of the CRISPR activation, it looks like a wild-type mice on the right, suggesting that this could be now a good therapy for over 660 genes and diseases on a single gene basis. Next. So what does it have to do with Angelman? So there's amazing work done by FAST to really target UBE3A and really amazing progress. It's been beautiful to see over the years. Next. But 90% of patients have a deletion, and in that deletion there's about 16 genes, next, and about 5 of them could be haploinsufficient, meaning they might have also a phenotype once UBE3A is rescued, next. And so the project that we are funded to is to try to upregulate, instead of one gene like I showed you, 5 of those genes all at the same time, next. And to get this as a therapy, we want to use an adeno-associated virus. And instead of what I showed you using basically one virus for one gene, next, we want to use one virus for 5 genes that will upregulate all 5 genes at the same time using this approach. Next. And so over the year, we've been going through all 5 genes here and individually and optimizing basically CRISPR-A conditions so we can upregulate them to therapeutic levels. Next. And so I'll show you one example, but we did this for all 5. This is for HERC2. And you can see we first transfect 5 different guides, and you can see that 3 work well here. Next. Then we make an associated virus for them individually, and you can see that 2 of them work well, and we select the best one that worked well. And we did that for all 5 genes. So we now have 5 genes that have very good guides that upregulate them to therapeutic levels. And so the next step is, will it work in one vector where we have all 5 guides together? Next slide. And the great news is that it does. So you can see here all 5 genes. And you can see that using 2 basically viral vectors, and one that has all 5 guides for those 5 genes, you can see that we're upregulating all 5 genes with these 2 viruses, and some a bit higher, some a bit lower, and that's some of the things we need to work on. But definitely it seems to work and could provide a potential therapeutic approach for those 5 genes. Next slide. So now that we have this working, we've already sent viruses, next, to Albert. Next, yeah. To Albert Kong, who is testing them on organoids that have the Angelman syndrome deletion, where he's going to rescue UB3A, but have just a deletion to look for phenotypes. And he's already optimized the viral conditions, and that is working nicely in these organoids. And so he's now going to try the 5 guides all at once in his organoids, and we're really excited and anxious to see the results for that. Next slide. At the same time, we're also next optimizing this for mice, so we could do this in mouse models, and we are working on getting similar thing, doing each gene individually. Next, and then we'll send those to Young P in Yale, where he has a mouse model where UB3A is fine, but all the other genes are missing. And we could test these in mice to see if this approach can rescue these phenotypes. Next. So just want to end by thanking my amazing lab, our collaborators, Albert and Young Hee, and FAST and all the patients and families for their support for this. It's been really great to work with you all on this project, and we hope to show more results in the next meeting. Thank you.
You still finished with time left over. Look at that. Awesome. Great job. Thanks for joining us. I know you're at another conference, and it's really a pleasure to have you speaking to our families about this exciting project. And this is a beautiful example to me of how you create resources. We funded Albert Kyung's lab at North Carolina State University, as well as Yang Wei's lab with different mice models, the large deletion specific mouse model at Yale University. We found Nadav, who's doing this really novel work in other disorders, and approached him to think about Angelman syndrome. And because he doesn't have the expertise in Angelman, doesn't have the cell lines, the organoids, or the models, he was much more inspired to work on this project because we had the availability of those tools and collaborators that were willing to work together. So he didn't have to create an entire expertise of Angelman syndrome that takes decades around this. He could be one piece of this. And that's exactly how we like to work. We like to work in collaboration and an integrative environment in which we can really get out of our silos and allow for rising tides to lift all boats. And as people learn and gain skill sets, they can share it with each other in order to really serve the greater mission, which is to bring treatments to children with Angelman syndrome. And so I thank you, Nadav, for taking on this project. I know this was not your life's work. We're going to make it your life's work, but we're grateful that you did it, and we're grateful to Albert and Young Wei and your teams for taking this on as well.